Hi everyone, this is Arohi and in this video I'll explain Inception V3. But if you are not familiar with the Inception version 1, then please go through it once. Link is given in description section. And let's start with Inception V3 now. First of all, let's see what are the modifications have been made in Inception version 1 to make it Inception version 3, right? So what are the changes? So let me show you what we have done in Inception version 1. So this is what we have done in Inception version 1. What we have done is we have added one by one convolutional filters. We have added one by these convolutional layers where we have one by one filter before this 3 by 3 convolutional layer and 5 by 5 convolutional layer, right? And what is the purpose? What was the purpose why we have added these one by one convolutions before this 3 by 3 and 5 by 5 convolutional? The ultimate reason is we want to reduce the number of dimensions, right? So that basically why we want to reduce the number of dimensions, because we want is that computational resources should be used less, right? So that's why we have reduced the number of parameters by adding this one by one convolutional layer, right? So what you can do, if again, how this one by one convolution is helping us reducing the number of parameters, that is given in my previous video on Inception version 1. Please go through it once. A link is given in description section, right? So this is what we have done in Inception 1. Now we'll continue from here only. Now we will see what are the changes have been made in this particular Inception 1 module, Inception 1 model, to make it more accurate for telling us the result, for predicting the results. So let's see one by one. So the very first thing is factorization into smaller convolutions. So now what is this factorization? Factorization simply means we will break the convolution into smaller convolutions. Let me show you with practical example. So this is the thing, okay, and let's call it Inception block A, right? The code which I'm showing you over here is, means what I'm showing you over here is, I'm telling you this concept, factorization into smaller convolutions, right? So we are saying it Inception block A. Later on we are going to use these blocks in our layer architecture when I'll show you the layer architecture of Inception version 3. There we will be using these blocks. Right now let's understand the code blockwise block, right? So what we are doing over here is, this is the same layer which I've just shown you. One by one convolution had been added before 3 by 3 convolution, and then again one by one convolution has been added before this 5 by 5 convolution. And the task which we want to do now is we want to factorize the convolution into smaller convolution. So we are working on this 5 by 5 convolution. What we are doing over here is we are replacing this 5 by 5 convolution with 2 3 by 3 convolution. Means instead of using this one layer where we are using 5 by 5 filter size, instead of that we are using 2 layers over here, 2 convolutional layer. Each layer will have filter size of 3 by 3. 3 by 3 into 2 means 2 layers. One layer and after that second layer. All right. So okay, now what is the reason why we have factorized this 5 by 5 convolutional layer into 2 3 by 3 convolutional layer? So the reason is, when you multiply 5 into 5 is how many parameters we are getting? 25. All right. And why we are factorizing it into 2 3 by 3? Because when you multiply 3 into 3 and plus 3 into 3, 2 3 by 3 filters. So how many parameters we are getting? 18. Right? By using one 5 by 5 filter, we are getting 25 parameters, and by using 2 3 by 3 filters, we are getting 18 parameters. Means the number of parameters reduced over here is 28%. And this is what we want to do. We want to reduce the number of parameters, right? And How we are reducing the number of parameters over here? How we are reducing the number of parameters? By factorizing, by performing a factorization on 5 by 5 convolution. We are basically breaking it into two 3 by 3 convolutions just to reduce the number of parameters, and by performing this, this inception block A, this is reducing the number of parameters by 28%, right? So I hope this code is clear now. And again, finally, we are concatenating the results of all the layers over here. All right. Now let's talk about next module. Now the next change which has been made in Inception version 1 to make it Inception version 3 is factorization into asymmetric convolutions. Now we have a convolution of 3 by 3, right? We have, if you'll see this see this picture again, we have a 3 by 3 convolution over here, right? Now we want to work on it. So what we are doing is, we are factorizing this 3 by 3 convolution into two asymmetric convolution. One is 1 into 3 and other one is 3 into 1. Over here 1 rows and 3 column, that means 3 rows and 1 column. Alright. So why we are doing this also? Again, we want to reduce the number of parameters, and how to know how many number of parameters has been reduced by using this method. So when you multiply 3 by 3, when you multiply 3 into 3, how many parameters we are getting? 9, right? And by using this asymmetric convolution, when you multiply 3 into 1 and then adding 1 into 3 in it, so how many parameters we are getting? 6. So over here, number of parameters are reduced by 33%. Again, we are reducing our number of parameters. And what is the second technique which we have used? Asymmetric convolution. The first technique is factorization into smaller convolution. Second technique used in Inception version 3 is factorize into asymmetric convolutions, right? Now let's see the block for it. This particular thing we have saved it in a separate block. This block is known as Inception block 3, right? So again, see over here, what was over here? Over here, if you see the very first picture which I've shown you, over here if you'll see, what we are having? 3 by 3 convolution. Now we will replace this 3 by 3 convolution with two different layers. Each layer will have like this 1 into 3 convolution and 3 into 1 convolution. Alright. And if you'll see over here also we are doing 3 into 1 and 1 into 3. Why? If you remember, in the very first block, Inception block A, we have converted this 5 by 5 convolution into 3 by 3 convolution. 3 by 3 convolution, and after that one more 3 by 3 convolution is stuck over here. Means the finally what we are having over here, same like this we are having 3 by 3 convolution over here also. That means this 3 by 3 convolution will also get factorized into 3 into 1 and 1 into 3 convolution. Alright, and again we are adding the results of each layer over here. So this is the code in Inception block C. See, now if you'll see, I have shown you the Inception block A and then I have shown you the Inception block C. Now let's talk about the Inception block B. See, in Inception block B also, we are doing asymmetric convolution only, but over here in Inception version 3, we are using a convolution of 7 by 7. Means we are having one layer where we are using a filter size of 7 by 7. Alright. And that we want to factorize. Now what we want to do over here is, we want to factorize that 7 by 7 convolution into this asymmetric convolution. Alright, so this is how this block look like. What we are having over here is, this is how it looks. See over here 1 into 7 and 7 into 1. Because over here we were having 7 into 7 convolution. Okay, that block I hadn't shown over here. This is the the solved block. So just assume over here, let's suppose we are having 7 by 7 convolution over here. So what we want to perform over here is 1 into 7 and 7 into 1. So that I've solved over here. And again assume here also we were having 7 into 7 convolution, and then I have performed asymmetric convolution, asymmetric factorization on that also, and we are having 7 into 1 and 1 into 7. And if you'll see over here, for these two convolution, I have written into 2. That means we want to repeat these two layers twice. Alright. So this is the block C. So, block B. So I have shown you block A, block B and block C. In block A, you performed factorization. In block 2, you have block C. Block C, you have performed this asymmetric factorization. In block B also we are performing asymmetric this factorization on the 7 by 7 convolution, right? So now we know about the 3 blocks. These 3 blocks we are going to use in our Inception V3 layer architecture. Now I'll show you the layer architecture of Inception V3. So let me give you a brief idea. First of all, this Inception V3 have in total, it have 48 layers in a network, right? And this Inception V3 model is trained on ImageNet dataset, not on using this whole ImageNet dataset, using some part of it dataset. Using means Inception V3 is trained on 1000 different classes, right? Means how many output classes we are going to have? 1000 different classes, because Inception V3 is trained on 1000 different classes. Now let me show you the layer architecture. So this is the layer architecture of Inception V3. So it accepts the input of size 299 into 299 into 3. Means colored image of this size. This particular layer architecture Inception V3 accepts the input of this size. And once you give this input to the network, see over here, convolutional layer. Okay, this is a convolutional layer where filter size will be of 3 into 3, and we are going to have 3 convolutional layers over here. First convolutional layer will have 32 such filters with stride 2, and filter size will be 3 by 3. And second convolutional layer will also have 32 filters of size 3 by 3, but with stride 1. Over here we are having stride 2, and over here we are having stride 1. Again we will be having convolutional layer where we are going to have 64 filters of size 3 by 3 with stride 1. And this will be the image size after passing through it. Means the image which is of this size, when we pass this image through these 3 convolutional layers, first convolutional layer will give us the image size this, second convolutional layer will give us image size of this, and third convolutional layer will give us image size of this. Why 64? Because we are having 64 filters. Alright. After that, we are having max pool layer where we have a window size of 3 by 3 and stride is 2. So the output from this is the output of these 3 convolutional layer, and this will become the input of this max pool layer. And when we apply 3 by 3 filter with stride 2 on this image size, this is what we get: 73 into 73 into 64. 73 into 73 means this is in height and width of image, and the 64 is the number of channels of that image, depth of image. Alright. And after that we have a convolutional layer, and the filter over here is, the size of the filter is 1 by 1. This 80 means 80 such filters. We want to run 80 filters of size 1 by 1 with stride 1, and this is what we'll get: 80. Now the depth is 80 because the number of filters over here are 80. Then it will go to the next layer. Over here we are having convolutional layer, and over here we want to run 192 filters of size 1 by 1 with stride 1, and this will become this size of the image. This is how you can calculate for the whole image. I've just given you an example solve for the first few layers. And then we have a max pool layer. Over here max pool layer is having 3 by 3 window size with stride 2. Alright. After that, if you'll see over here, this is important: Inception block A. Into 3 means we will run this Inception block A 3 times. Means Inception A, then again Inception A, and then again Inception A. And what is the code in Inception A? If you are familiar, if I've just explained you a few minutes back only, this is the code in Inception A. Means we will run this block 3 times over there. Alright, and we are running this block 3 times over here, and after that, if you'll see, we have one more block with the name of reduction A. I'll come to this. I'll just explain you few minutes. Just give me few more minutes. I'll explain you what is this reduction A. But after that, see what we are having. We are having Inception block B, and how many times we want to run this block? 4 times. And what is there in Inception block B? This is what there is Inception block B. This I already explained you what is there in this, right? So basically what we are doing over here is we are factorizing 7 by 7 into a asymmetric factorization, right? So this block will be here for 4 times. And then again we are having reduction B. This I'll explain you what is this reduction B, right? But after that we are having Inception block C. And we want to run this Inception block C how many times? 2 times. So I have explained you Inception block C also. This is what Inception block C is, right? So we are performing that over here. And then we are having average pool layer. So now we are having, see, these are the fully connected layers, right? Dense layers. So we are having 2 dense layers. One layer is this and the other one layer is this. So over here also, if you'll see, in between the layer architecture, we are using a classifier over here also, right? And we are using classifier here also, and we are using classifier in between the layer structure also. Now what we are basically doing over here? So just see, this S means softmax, this B means batch normalization, R means ReLU activation function, and S means softmax activation function, right? So these final layers are the classifiers, right? And we are having 1000 neurons in it. Why we are having 1000 neurons in it? Because our algorithm is trained on 1000 different classes. So to predict the results, we need to have 1000 neurons from the output class, right? This is a classifier, right? But before that, if you'll see here also and here also, we have one more classifier over here. These fully connected layers, these dense layers are also called auxiliary classifiers. Now first of all, let me explain you what is auxiliary classifier. See, here we are using this auxiliary classifiers before the softmax classifiers. We are adding this auxiliary classifiers to tackle the problem of vanishing gradients. Alright, the loss of auxiliary classifier is used to overcome the vanishing gradient problem, and basically, see, it has nothing to do with prediction. Alright, we are using auxiliary classifier because we want to overcome the problem of vanishing gradient. There is nothing to do with prediction. For prediction, see, the prediction is made by the final classifier only, the softmax classifier, where we have 1000 neurons, right? 1 neuron for each class, and the Inception model is trained on ImageNet. I've just told you, right? This Inception model is trained on ImageNet for 1000 classes. That's why we are using 1000 neurons in last class. See, in Inception V3, one auxiliary classifier is inserted in between the layers. If you'll see, in between the layers, we have inserted one auxiliary classifier over here also, right? So what is the reason behind it? Why we have added this auxiliary classifier why we have inserted this in between the layers? Basically what we are doing is, for training time, we are inserting this auxiliary classifier, and what we want to do is we want to calculate the loss from this auxiliary classifier, and we'll calculate the loss of this auxiliary classifier, and then we'll add it to the main classification loss, right? Means we'll in between the process only, in between the layer structure only, we are using this auxiliary classifier because we want to remove the problem of vanishing gradient. We will add the loss of this auxiliary classifier while, to the main classifier, just to improve the results. right? So I hope this is clear why we have added this auxiliary classifier, just because we want to solve the problem of vanishing gradients. All right, so let me tell you what is this reduction A and reduction B. So these are again two blocks. Let me show you the blocks. Okay, where are these blocks? Reduction blocks. Okay. So this is reduction block A. So what we are doing over here is basically, this is max pool, and over here we are having 3x3 convolution, and over here before this 3x3 convolution we are using this 1x1 convolution, and we are repeating this 3x3 convolution twice. So if you remember, when we repeat this 3x3 convolution twice, when we have a filter size of 5x5 convolution, at that time we factorize that 5x5 filter into two 3x3 convolution, right? And what will happen by that? By this 1x1 convolution also will reduce the number of parameters, and by factorizing that 5x5 filter into two 3x3 convolution, again we will reduce the number of parameters, and finally we are concatenating the results. So this is the code which is there in reduction block A. In the same way we have reduction block B, and this is the code in reduction block B. So what we are doing over here is we want to replace the 7x7 convolution into a 3x3 convolution. All right, so this is what we are doing. So these are the layers, and this is the main code which we are performing in this 1 into 7 convolution and then 7 into 1 convolution. So what is this? This is a asymmetric factorization, and after that we are converting, after that we are using 3x3 convolution over here. So this is what there is present in this reduction blocks, right? So I hope you are clear with the this layer architecture of Inception now, Inception version 3 now, right? So in short, in conclusion, what we have learned is basically, see, first of all we are using different size filters parallelly to capture the information in image, and then we are factorizing the filter to reduce the number of parameters, by which we will reduce the computational resources also, and then we are using the auxiliary classifiers to prevent the problem of vanishing gradients. So this is how Inception version 3 gives us the better accuracies as compared to the other image recognition models which was developed before it. I hope you like this video, and guys, if you like the video, please subscribe to my channel and share it. Thank you.